Okay, so today we're just going to finish up recursion, and then for the rest of the semester it will be, well, not for the rest of the semester, but when we come back on the next week, then we'll start on one of the last major modules, which is going to be searching and sorting, which is going to take a little more than the usual week that we cover modules in. Last time we did this, I gave you a motivating demonstration where we had a little challenge of printing a countdown, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off, but we weren't allowed to use a loop. And the way that we solved that was by using recursion, by creating a function that called itself. And in the context of code, that's what recursion is. In general, recursion is anything that has a self-reference. Again, in coding, a function is recursive if it makes one or more calls to itself, right, to the same function. And we saw the visualization of that where the way that it works was by creating new stack frames on top of stack frames on top of stack frames in order to, you're basically abusing the call stack in order to do a loop, right, or to get the same effect as a loop. It's not just in code, though. You see this all over in mathematics and even in language, right? Recursion, me, myself, and I. That is a way for you to refer to yourself, right? You don't refer to yourself in third person. You generally use those pronouns. Now, in mathematics, you can also see, fractals. Mathematics, right? Fractals are self-similar objects. And you probably have seen these before with fractal art, right? The Mandelbrot set or the Sierpinski triangle. If you just do a Google search or image search for, the Mandelbrot set, right? It'll come up with a bunch of, fractal art kind of stuff where it's a self-similar object. The easiest way to visualize this is maybe the Sierpinski triangle. Where you start out with a triangle, and then you cut out a triangle in the middle, and then you recursively do that operation over and over again. On the top triangle up here, you cut out the middle one again. Then you recurse on the three remaining triangles, cutting out the middle, recurse on those three, but you do it infinite, right? You do it, you don't stop. Each one of these pictures, of course, is a finite object, and so it's going to be a finite recursion. But fractals are an infinite object, and it can lead to really weird stuff where you have dimensions that are between integers. For example, a line has one dimension. A square has two dimensions. Right? A box or a cube has three dimensions. Each one of these fractals has a dimension that is somewhere in between there. So, for example, like a dimension of 1.5 or something like that. Right? And it's because of the way that these are defined in continuous mathematics and all that stuff. It goes way beyond the scope of this course, but it's the same idea. It's recursion. It is self-similar kind of self-reference kind of stuff. Let me make sure that this is working. Yep. So again, if you have any questions, we are on Piazza and we are on YouTube. Go ahead and please post there. I'll make sure that I'm watching Piazza. There we go. Another instance which you've probably seen before, and it's a great instance, and it's a terrible instance, is the Fibonacci sequence. Right? Anytime like 99% of the coding courses I've ever seen, when they introduce recursion, they always go to the Fibonacci sequence. And it's ironically, it's simultaneously the worst possible example that you can give, but it's also the best possible example that you can give of recursion because it illustrates exactly why you don't want to use recursion. Okay? So why is it a good kind of example? It's because it's easy to understand, and therefore it's easy to take the definition of the Fibonacci sequence and easily code a recursive solution for it. Now to motivate this, we're going to go ahead and do that as an exercise. Let me go ahead and bring this over. I'm going to go ahead and modify it a little bit. There we go. So there's the Fibonacci sequence. Now don't worry about that definition there. Worry about the sequence. It starts with 1. Then the second number in the sequence is 1. Each number after that is the two previous values in the sequence summed up. So for example, let me go ahead and start writing out what the sequence actually is here. So again, the first two values are 1 and 1. The next value is the two previous values summed together, so 1 plus 1 is going to be 2. The two previous values summed together is now 2 and 1, so it's going to be 3. The next two values, or the two previous values are now 5, 8, and you can start to see the pattern here. What's next? 13, right? You can all add, right? 21, 34, 55, and 89, dot, 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 right? Why dot, dot, dot? Because it's an infinite sequence. It goes on forever. And it grows quite quickly. It grows exponentially, okay? Let me go ahead and give myself some more room here. There we go. All right, so it pops up there. So it's a good kind of example because it shows you how to write recursive functions, okay? So we're going to do that now over here in my CS50 IDE. Let's go ahead and write a function called Fibonacci, right? That takes an input and returns an output. It'll take an input here that is n. I want to know the nth Fibonacci number, right? That's the definition over here. Instead of f, it's Fibonacci of n. I want the nth one. So if you wanted the 10th one, or is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10th one would be 55, right? Because the sequence starts at 1, 2, 3, 4. Those are the indices of the sequence, okay? What should my return type here be? I could do an int, but I want to illustrate this for very large numbers, so I'm going to show you it for a long, right? A long is a 64-bit integer. It can represent numbers up to 2 to the 63 minus 1. Minus 1 because it needs a sign bit, and also it's signed, so you go to negative values and positive values, okay? So let's go ahead and write this function. Actually, let's first of all, let's make sure that we have a test case for this function. I'll go ahead and say int n is equal to, I want that 10th Fibonacci number. Long result is going to be equal to a call to Fibonacci of n. And then we'll print it out. Printf Fibonacci of %d is equal to %. Now the way that you format a long is just LD, long decimal, right? And then the line, and then n, and result. Okay? You'll be working with longs not this week, but next week in your hack on recursion. Right? All right, so let's write this function now. To do that, I'm going to go back and look at this mathematical definition. If n is equal to 1, what's the value of the number of the sequence? 1. If n is equal to 2, what's the value of the sequence? 1. So let's take care of those first. If n is 1, or if n is 2, then I'll return 1. Technically, you should do 1L. That distinguishes it between a regular old integer and a long integer, but the compiler won't care. Right? But that is a way that you can do it. 1 lowercase l here. Right? In fact, I think, yeah, let's go ahead and try that. GCC, main, GCC, Fibonacci, come on. Yep, it's happy even without the L. I'll go ahead and leave the L in though, just in case you have a compiler that requires that or something. Right? Now, before we look at the main showdown here, is it defined for any n value that is negative? Remember when we did countdown and we started 10, 9, 8, 7, 6, 5, 4, 3, 2, 1? It still worked when we went up to 20 and then counted down to 1. But did it work, initially at least, when we started our countdown in negative values? No, we hit an infinite recursion. And eventually, we had a stack overflow. So what should I do in that situation here with Fibonacci when it's not even defined for negative or for 0 and negative values? I could put that in as a corner case. If n is less than 1, I'll return something, right? Else if it's 1 or 2, then I'll do something. Otherwise, I'll do something else. And that's the main show here. So what should I do here? Should I return 1? I could return a flag value here, -1. Right? I could return 0, right, and just put it in my documentation that upon invalid input it returns 0, or upon invalid input it returns 1 as a flag value to indicate that error handling. Okay? Otherwise, I'll return 1. Now here's where the main show comes in. I'm going to make a call, a recursive call, to Fibonacci of n minus 1, and another recursive call to Fibonacci of n minus 2, and I'm going to add those two things together. Right? So I'll go ahead and return Fibonacci. I don't need to restore. I don't need to store it into a temporary variable. We will later on because we'll want to, but I won't do it here. I'll make it look exactly like the mathematical definition. N minus 2. Right? All I'm doing is having this function call itself, but on a value that is 1 smaller, or on a value that is 2 smaller, making progress towards one of these two base cases. Right? And this is why it's always used as the de facto example when presenting recursion. Because it is so easy to write, it is so easy to, I mean, it's virtually the same thing as the mathematical statement over here. It just has some additional syntax. Let's go ahead and make sure that it works first of all. I'll compile it, I'll run it, and we should expect 55, right? I think, yep, excellent. Right. Let's go one more, and we would expect 89. Right. That's the 11th Fibonacci number. Okay, let's go one more, just to make sure that it, absolutely sure that it works here. What would be the 12th Fibonacci number? 55 plus 89 is 1, oops, sorry, I need to recompile. That would be what? 144, all right, great. We call that a gross, right? Everybody knows that? A dozen is a gross, right? If you didn't know that, then you learned something today, other than what I'm talking about here. All right, so it seems to work. So let's go ahead and see what kind of mileage we can get out of this. What's the 100th Fibonacci number? It's pretty large, right? Not that large though. All right. Well, I want to make sure I'm not going to manually do this. Instead, I'm going to appeal to something else and ask Wolfram Alpha, what's the 100th Fibonacci number? All right, so it's large, but it's not that big. It's quintillions, right? And I do believe that you can fit this into a 64-bit long. I'm not sure. But in any case, it should be done by now, right? How long do you think I should wait? Just give me an estimate. Should this be done in a few minutes? Should this be done in a few hours? No? Go ahead and throw out an estimate here. 30 minutes? Okay. So Domino's pizza delivery time? It should be faster than that now, right? All right. So why is it taking so long? We'll let it run, and if it does it in a few minutes, then great, successful, whatever. Let's understand what's going on here and why the Fibonacci, the traditional example that's always given, is also a perfect example for why you don't want to do recursion generally. Let's just take one example here. Fibonacci of 7. Right? How is that computed? That will make two calls. One to Fibonacci, and I've shorthanded it here to fib, and I'll shorthand it even more in a second here. It'll make one call to Fibonacci of 6 and one call to Fibonacci of 5. Okay? Fibonacci of 6 and Fibonacci of 5. Right. Fibonacci of 6 makes two recursive calls because we're not to our base case yet. That makes a call to, and here I'll even shorthand it even more, 5 and 4. Fibonacci of 5 will make two recursive calls to 4 and 3. 5 goes down to 4 and 3. 4 goes down to 3 and 2. 3 goes down to 2 and 1, 2 goes down to 1 and 0. And by the way, at this point, that's one of the base cases, so there's no more recursion. Sorry. You're right. I did adjust it to be 1 and 2, so there. There. Okay. We'll only go down to 2 here. 2 and 1, right? 3 will go down to, or 4 will go down to 3 and 2, at which point it stops. 3 will go down to 2 and 1. 4 will go down to 3 and 2. 2 and 1. 2 and 1. There we go. So, how many times did I call Fibonacci of n, for n being 7? Number of calls. In total, you add them all up to 24? All right. What about 7? I just made one recursive call, or one call. But 6, that's also 1. How many times did I recompute a call to Fibonacci on an input of 5? 1, 2. Okay. How many times did I make a call to Fibonacci on an input of 4? 1, 2, 3. Without even looking at this and without even pointing out all of them, what about 3? What do you think? 5. 2 and 1? 8 and 13. Does that look familiar? That is the Fibonacci sequence right there. And if you sum them all up, did you say 21, 22, 23, 24, 25, 33 total function calls? Is that right? I'll just question mark that. Right? Do you see how inefficient this is? Because I'm calling the same function on the same input over and over and over and over again. Yeah?
Where are you getting the 13 calls to 1?
Oh, was it not?
Well, it still calls the 1. It just
1, 2, 3, 4, 5. Oh, did I not? Oh, okay. Sorry. What about 2? 1, 2, 3, 4, 5, 6, 7, 8. And then this one is, okay. Star. It's a special case. Right. So don't worry about that. What did it end up being? 1, 2, 3, 4, 5? 5. And then what is the actual number? I don't know. It's just large. Right? Now, imagine doing this for 100. Right? How many function calls will I be making? Roughly 354 quintillion function calls. Okay? That's just an estimate, right? Still going, right? How long will that take me? Let's just say that that's the number of function calls I do. Let's say that that's the number of operations I do, just to keep it even simpler. Anybody want to humble brag on their rig? Anybody have a 3080 Ti? All right, a 3080. 3070? 2080. 970. We're talking about 2060. All right. How many floating point operations per second does your card is able to perform? Well, let's be generous. Let's say that it's there's 1 million. Is that 1 million? 10 million. So 1 million. 1, 2, 3. 1 billion. 1, 2, 3. Let's just say 1 trillion. Right? That's way overestimate, by the way. Right? So we're being very, very generous to your rig right now. Right? That's floating point operations per second. There are 60 seconds in a minute. There are 60 minutes in an hour. There are 24 hours in a day and 365.25 days in a year. Even if I were to run this program that's currently running on Amazon Web Services on your computer with a huge overestimate on its power, that's the number of years you would be waiting for it to compute. Now again, I was overly generous here. Let's go ahead and kick that down in order of magnitude. Right? And you're talking about 11,000 years to wait for this to run? Do you have an estimate? Or what did you say? Okay, that's all right. Anyway, should I be waiting for this? No. Right. So let's think of an alternative here, at least for the Fibonacci sequence. Should I be using recursion to compute the Fibonacci sequence? And here's why it's another terrible example. How many people in their daily lives need to compute the 100th Fibonacci number, right? It is not a practical example at all of recursion, right? It is a toy example at best. Not only that, but the Fibonacci sequence is associated with all these mystical things like the golden ratio and, ooh, there's this it's nothing. It's nothing more than a homogeneous linear recurrence relation of degree 2. And there's no shortage of those, right? It's just an equation that somebody gave a name to and that people have glommed onto over the centuries. Right? It's nothing special. It is nothing practical, okay? But let's go ahead and resign ourselves to an interview question here and do this as an iterative version of the Fibonacci sequence, int n. Right? So how would I do this iteratively instead? Actually, I'm going to go ahead and go with previous and int current 1. All right. What am I doing there? I'm keeping track of the two previous values because I want to add them together, right? So what am I going to do? If I've got these two values here, I want to add them together for the next value, right? So int temp is equal to previous plus current. Now what do I need to do if I'm keeping track of the two previous values? Current is equal to, actually, I need to go previous is equal to the current. I'm moving this one over here. I'm throwing this one basically out. And I've got this temporary variable that I'm going to move into current so that I'm moving these two variables along and always keeping track of just two variables. So previous is equal to current and current is equal to temp. But I need to do this over and over again. How many times? I'll start at, say, 1. I is less than equal to n, okay. And I'll do these 3 operations. Now, I might be off by 1 here, I'm not sure. We'll go ahead and test this out by returning the current. All right? And instead of, I can't call this Fibonacci, can I? Nope, I'll call it Fibonacci iterative instead. And let's go ahead and call that one instead. I might be off here, but we can always fix that. Oh, not 100, but let's fix it, do it for something that we know is correct. I should expect the 10th Fibonacci number to be, what was it, 55? All right, we're off by 1 here. So there we go. There. Oh, wait, I'm off by 2. I'll start at, I'll go minus 1 there. Because I'm going 1, 1 here, so I'm already starting at 2. G, 55, there we go. Let's make sure, what was the 12th one? That was 144, right? Yay, okay. And if I try it for 100, I'm not sure that I'm going to get the right answer because it might be overflow. This might still be too big for a 64-bit long integer. But let's go ahead and try it anyway. Yep, I get the wrong answer, but at least I get it quickly, right? And that's definitely overflow here because it's negative. Good question. That loop will never execute, so we'll probably get 1, right? And 2, we should get 1 as well because it will not execute, or will it? Yep. And that edge case there of negative, I could just bring that down here and immediately return with it. Right. So that if you do give something that is negative or 0 or whatever, then you get that flag value. Right. Let me clean it up. There we go. All right. So that is one of the keys of recursion. Take any computable recursive function and you can always write a for loop for it, or a while loop. Right? Just as you can take any while loop and rewrite it as a for loop, and a for loop and rewrite it as a while loop, you can do the same thing for recursive functions. In fact, there are programming languages that don't allow recursion. Very, very early versions of Fortran or COBOL or something like that didn't allow you to have a function that called itself. Lots of style guides will, even if your language supports recursion, lots of style guides will say, do not use recursion, use something else, because of the risk of stack overflow, especially in embedded systems or very system critical things. For example, NASA. NASA in a lot of their projects will forbid the use of recursion because of its risks, right? And especially in embedded systems areas. So let's go ahead and talk about that. Let's go ahead and review what we just did, all right? When you're writing a recursive function, there are basically the same aspects in a recursive function as there are in a loop. You have your starting point. How do you start the recursion and how do you get it kicked off? Well, you call it with a particular input, in this case, right? When I called Fibonacci of n, I gave it an initial input. That was my initialization. You also have one or more base cases. That's your termination condition in which you make no more recursive calls. Just like a loop has to stop at some point, you need the recursion to stop at some point so that it goes back up. Otherwise, it's an infinite recursion, and you will have stack overflow. Right? Some base cases may be for error handling, like we just did. Right? If it's outside the range of acceptable values, we can do nothing at all, not even recursion, not even the other base cases, and simply just return a flag value. You can make one or more recursive calls, but you have to make progress towards your termination condition, towards your base condition. Just like a loop has to make progress towards that termination condition, or you have an infinite loop, you have to make progress towards your base case, or you have an infinite recursion. Right? Is it good? Is it bad? It certainly is ugly, right? At least in my opinion. Right? So what's the good of recursion? Recursion can be useful or good. Right? So let me play the devil's advocate here. This is not my take on it, but if somebody were advocating the use of recursion, here's what they would usually say. Many divide and conquer style algorithms will be presented recursively. Right? It is a good way to think inductively. Right? Induction is a fundamental mathematical tool used to prove things, and induction is also a fundamental way of thinking about algorithms. Because you are given the current state of the algorithm, and you have to think about what's the next step. You do this all the time in your loops. In your loop, on one iteration, you have a state. You have an iterator variable. If you're summing something up in an array, you have the current sum. How do I get to the next step? Here's my current step. How do I make progress towards the next step? That's thinking inductively. And recursion is a natural way of thinking inductively. When we move on here to searching and sorting algorithms, we'll present a lot of these algorithms as recursive, although I'll also implement them non-recursively. Right? Many functional programming languages encourage or primarily use recursion. Right? If you're interested, Pascal, Scheme, Lisp, right? Those are the main functional programming languages. Even something like Python has functional aspects to it. In fact, most programming languages have had functional aspects added to them later on, the useful parts. We won't get into that now because C is not one of them, of course. Right? Recursion can also lead to simple or clean, or if you are used to thinking in terms like this with the Fibonacci sequence, then yeah, I would absolutely agree with you that it leads to simple code, or clean code or beautiful code, because it doesn't get much more simple than taking this and directly applying it over here. Right? There's almost a one-to-one correspondence between these two things. Right? But one person's simple, one person's clean, one person's beautiful, is another person's complex, another person's ugly and dirty code, right? These are all subjective kind of measures, and that's why I don't agree with them. Why is recursion bad? And so now I'll put on my own hat and give you my own opinion here. Why is it bad? Recursive functions are essentially abusing the call stack and risking stack overflow. Even on very simple stuff, you can risk stack overflow by making too many recursive calls. You risk recomputing values over and over, just like with the Fibonacci sequence. Okay, I'm going to show you a way to mitigate that. Right, you risk a naive exponential approach to a problem. So there are lots of risks here, all of them dealing with performance. And performance is certainly an objective measure rather than these other things that are certainly subjective arguments for recursion. Right? Now you might get somebody to come in and give you a different perspective. If you've seen recursion before, say in Java or whatever programming language, if you have had programming languages before, maybe you were presented it in a more positive light. Sorry, yeah, I'm giving you the bad parts here. Right? So let's look at a best of both worlds kind of scenario. All right, I'll give a little to those who say that recursion is awesome. All right, let's go. But they also need to give me a little bit in the sense that recursion risks a lot of recomputation and a lot of inefficient computation. So let's meet in the middle here by either eliminating recursion or reducing the risks of those recursions. Right. So again, in general, any computable recursive function can be replaced with a with an iterative solution. You can basically, instead of abusing the call stack, you can use a stack data structure to simulate the recursion, and then you're not making any recursive calls at all. You can use various tricks to eliminate the additional function calls, including using a stack or using what's called tail recursion. And I'm not going to get into this, but basically it's a compiler optimization thing. The compiler can see that, wait a second, you're using that call stack and you're only ever using it to store the parameters. For example, like the countdown. You remember the visualization that I gave you last time with the countdown? It was just 10, and then 9, and then 8, and 7, 6, 5, 4, 3, 2. It was only keeping track of that parameter value. There were no local variables at all. Right? It was decrementing it each time and then handing off a new copy to each call. And the compiler can see that and say, wait a second, you don't need a call stack like that. Instead, I'm going to optimize that away and take out your recursion, and I'm going to give you a loop to do that. It translates your code into an iterative version automatically. And if you use tail recursion, then you can rely on the compiler to take care of that for you, right, in certain circumstances. Or you can use what we're going to use, memoization. That is not a misspelling. I did spell it correctly, and I did pronounce it correctly. Right? It is not memorization, it's memoization. So one of the problems with the Fibonacci sequence that we just computed was that it was computing the same values over and over and over again. Right? So if you need to compute a value, go ahead and do so recursively, paying for the recursion. Right? But once you compute one value, store it, right? Or here's the word that we'll use, cache it, and save it for later. Right? Before you do a subsequent recursive call, check your cache. If the value has already been computed and stored, use it, avoiding the recursive call. Cool, right? So in that big giant exponentially sized computation tree that I just drew with Fibonacci, what does it look like now? Well, if I can pull it back up. Just a second. There we go. All right, so this can be seen as a tree. In computer science, trees grow downward because trees represent data, and we read top to bottom, left to right. So this up here, this is the root of the tree. Down here, these are the leaves of the tree. Right? But you can see that it's exponentially sized. Why? If I start out at the root here, and I have 2 branches, I have 2 more branches, 2 more branches, 1, 2, 4, 8, 16, 32, right? We're growing exponentially, powers of 2. So let's go ahead and take a look at things that I have computed more than once. For example, Fibonacci of 5. I computed it here and here. Suppose that over here was the first time that I computed it. I paid for the recursion. Don't pay for it again. Store that value off into some cache. For us, that's going to be an array. And then don't recompute it over here. What have I essentially done? I've taken this entire subtree and I've cut it out. When we cut off a branch of a tree, what do we call that? Trimming a tree or pruning a tree, right? Because we don't want to trimming the tree or trim the tree. Trim, prune. We in computer science we usually call it prune. Right? I'm not an arborist, right? So I don't know. Say what?
Pruning is usually for like the plant's health to help it grow.
Oh, okay. Well, this is for its health, right? And then trimming is you want to kill it.
Pruning is just making it look nice.
Okay, trimming is making it look nice. Pruning is for its health. All right, I like that. All right, so what about 4? Well, the first time I computed is over here, so don't recompute it over here. Trim that tree out, right? Or prune that tree out. What about 3? Cut that right there. Right? And of course, 2 and 1. You don't have to cut. You don't have to do this subtree here. My tree is looking rather thin now, right? It's only these parts right here, right? It's not. It's less of a tree and more of a what? A stick, right? So you've basically cut out most of the tree here, and you've cut out most of your computation by keeping track of previously computed values. What does that look like in C, right? Well, let's come down here to the main, and I'm going to rename this as Memoization, right? And we're going to have to write this now, okay? I'm going to go ahead and bring it up here, long, now, Fibonacci with Memoization, int n, and maybe something else too, okay? In fact, what should that something else be? I want to keep track of these values, okay? How do I store these values? Yeah, an array. That's the only storage mechanism that we have so far, right? Is an array. So actually long star, and I'll call this my cache because that's what it is, right? Now we'll figure out what the entries of this cache should be later, right? But otherwise, it should look something like this. Right? It is still going to be recursion, right? If you don't have the value stored in the cache, then you need to pay for the recursion, okay? So we can keep these. Let's go ahead and write that logic here now. All right. So if it's invalid, then we'll go ahead and just return with that flag value. It doesn't matter. Else, if the value of Fibonacci of n has been computed, use it. Return the value. Right? Now, of course, this is not real code. Help me out here. How can we determine whether or not the value has been computed or not? Well, it's in this cache, right? So how could I set up that cache so that I can look at the value at a particular index, say? If the cache at index n is been computed, right? Has been computed, then return that value in the cache. So what if it's a valid value, then it has been computed, okay? If it hasn't been computed, then it'll be an invalid value. So if it's not equal to, give me a value that would indicate that it has not been computed yet. What value are we using over here to indicate that it's an invalid input? -1? So if it's not equal to -1, then we know that we've computed it at some point. Okay? Else, what I'll do is it has not been computed. So pay for the recursion. ... Right? I'm going to now here's where I am going to store them into values. Long A is going to be equal to Fibonacci of memoization of n-1 passing in the cache. Right? Long of B is equal to Fibonacci memoization n-2 passing in the cache. And then those functions are responsible for looking in the cache to see if n-1 has been computed or if n-2 has been computed. And if so, returning those values. Right? Otherwise, my new result here is going to be A plus B. Now, I've computed it. I've paid for the recursion. I want to make sure that I never pay for it again. How do I do that? By putting it into the cache before I return it. Okay? The rest of this is unnecessary now. I'm returning in all three of these blocks. Now, the key here is to set up everything up here in your main. Right? So I've got n here, say 10. Right? I want to compute the 10th Fibonacci number. How big of a cache do I need? I want 10, right? So I would start it at what? 0, which is undefined. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need an array, a cache of size n plus 1. Right? This has nothing to do with the null terminating character because these are not strings. All right? So long cache is equal to long star malloc size of what? Long times n plus 1. I'm making it 1 extra because I want all my indices to line up. Cache of 0 is going to be undefined because the Fibonacci sequence of 0 is undefined. Right? Now, is that enough? Have I set my cache up for the expectations that I set up here? Are all the default values -1? I haven't computed anything yet. Right? So let's go through that cache and make sure that I am setting it up properly. For int I equals 0, I is less than n plus 1, I plus plus. Set your cache values of I equal to -1. Right? The ith Fibonacci number has not yet been computed. ... There. Okay. What else do I need to do? Up here in this new version that I wrote, do you see any base cases? Nope. I mean, there is a base case here of if you've already computed it, but I need a starting point now. If it's 1 or 2, I need to set that to 1. So let's take care of those. Cache of 1 is equal to 1. Cache of 2 is equal to 1. I'm setting those base cases here. Set the base cases before the recursion. I could do that in the function if you really wanted to, but I'll just go ahead and set them here. Okay. Now it's with memoization and I pass in the cache. There we go. Let's see if it compiles or if I screwed up somehow. All right, compiles, great. I still set it equal to 10, which remind me now, what's the 10th Fibonacci number? Is it 55? There we go. It was instantaneous. Let's try it again with 12. That should have been what? 144. So I'm convinced that it's working, but now let's go ahead and again, let's set it up to be 100, right? GCC, there you go. And again, I'm getting probably the wrong number, but at least I'm getting it fast, right? So here, I don't know, is this, is this less than 2 to the 63rd minus 1? Is that true or false? It's false. So let's go ahead and try to figure out what the 60th Fibonacci number. Let's see if that'll fit. That looks like it'll fit. Is that less than 2 to the 63rd minus 1? That should be true. Good. So we can do the 60th. And then we can benchmark ourselves. Right? Right? And that looks like that number to me. You agree? So I'm fairly sure that it's correct. Now all we need to do is, well, what would happen if instead of Fibonacci memoization, we called our old naive Fibonacci without memoization? Oops. What? Say what? Oh, there's no cache. Thank you. All right. Yeah, probably not 11 or 11,000 years, but certainly not within probably even a week. Right? So, questions on that? Yeah, go ahead. Oh, it'll be just as instantaneous, I'm sure. We can kill it here and go with iterative. Right. There. And what was, oh, is it wrong? Oh, why are you wrong? And oh, is this the 60th Fibonacci number? Did I screw something up in the iterative version? Looks like I'm off by 1 or something. I don't know. Iterative. Oh wait, no. No, I am off. So I screwed up somewhere on the iterative version. Is it? I am off by 3 million. Exactly, huh? Oh, duh. Here's why. Long. Make sure that everything is long. There you go. That looks way more like that number. I'm not going to look at every single digit, but 1548 is good enough for me. There we go. Got to have the correct types there. Otherwise, it was overflowing, and that's the reason why. In fact, it was overflowing and then overflowing again to come back to the positives. Okay. Then, not this week, but next week, you will be applying this to hack 12. Right? So just to make sure that we're all on the same page here, there is some information in the handout here, but you'll be doing some basic combinatorics. Instead of the Fibonacci sequence, you will be doing binomial coefficients. N choose k. There is a nice formula here based on, what is this thing that's shouting at you? That's a factorial right there. A factorial, n factorial is n times n minus 1 times n minus 2 times n minus 3, etc. So, for example, what is 6 factorial? It's 6 times 5 times 4 times 3 times 2 times 1. Anybody know what that is?
720.
Is it 720? There we go. 5 factorial is 120, so yeah. All right. So what is n choose k? This should be read as n choose k. And it's got this nice formula here in terms of factorials. I'm not going to derive the formula. All I'm going to do is give you an understanding of what this is counting. Right? So let me go ahead and give you, say, 4 people. Right? N equals 4 people. Alice, Bob, Clarence, and Darlene. Right? I'm not going to remember those names. So we're just going to call them A, B, and C, and D. Right? I want to choose 2 of them for a 2-person team. Right? I'm starting out with 4, and I choose K, 2 of them, For how many possibilities are there now? I could pair Alice up with Bob, A, B. What about pairing Bob up with Alice? That's the same thing. This is an unordered combination, right? What else could I pair up? I could pair up Alice with Clarence. Thank you. I could pair up Alice with Darlene. So that's all the possibilities with Alice. I can't pair up Alice with herself. It's got to be two distinct people. Right? So what else could I pair up with? Bob with Clarence, Bob with Darlene, and finally Clarence with Darlene. And again, switching those back and forth, that's the same pairing, right? There's not a leader and there's not a follower. It's just it's a pair. Okay. How many was that? 6. In other words, 4 choose 2 is equal to 6. All you have to do is look at this first formula here of n factorial is going to be 4 factorial over 4 minus 2 factorial, in the denominator 2 factorial, which is equal to 4 factorial is what? 4 times 3 times 2, so that's going to be 24. 4 minus 2 is 2. 2 factorial is 2. So 2 times 2. We call that 4. And so it's 6. Right? And so you see, oops, sorry. Duh. Sorry. I was not showing you, I was not showing my work properly there. So 4 factorial, 4 minus 2 factorial, 2 factorial, and that comes out to 6. Exactly as many as we derived over here by thinking about it. Right? Now, in general, you could have 100 students, and you want to split them into two groups, so that one of them can take their final on Monday, and the second group can take their final on Tuesday. Right? That's going to be 100 choose 50. How big is that? 100 choose 50. That's going to be huge, right? That's even bigger than the 100 Fibonacci number that we just did, right? And you may or may not be able to store that in a long, right? We give you information on what's the maximum value you can actually store in this stuff. But in any case, this is the iterative version, right? And I think that we give that to you for verification purposes to make sure that your code actually works. But over here, this is called Pascal's identity. And it's a recursive version. If you want to compute n choose k, all you have to do is go n minus 1 choose k and n minus 1 choose k minus 1. Just like Fibonacci, and add those together, and that's your result. In other words, instead of a bunch of factorials and multiplications, all you have to do is make 2 recursive calls to a function decrementing either n in one case or both of them in another case. So this leads to a very, very easy recursive function. The problem is the same as Fibonacci. You end up recomputing a lot of values, and it will not execute within your lifetime if you do it naively. Instead, you need to use memoization, and you'll be doing that in Hack 12. Again, it's the number of ways to choose k elements from a set of n without any consideration on the order. So it's very, very useful. They're called binomial coefficients because they're in the expansion of a binomial polynomial, x plus y raised to the n. If you expand that out, all the coefficients in that expansion give you can be computed with n choose k. And then you can come up with another nice, beautiful mathematical thing called Pascal's triangle. Right? That looks something like that. Those are the coefficients. That's all you're going to show me? Oh, here, more rows. Oh, that's all. Oh, come on. All right, but anyway, it's an infinite triangle. Right? All right, any questions? No? So on Monday, we'll start on searching and sorting then. Right? All right, have a good weekend.